Okay, this is number theory, lecture 6. And I was just asked to solve the following problem. This is in section 1.3, number 12, which has to do with continued fractions. So we're given the continued fraction A0, A1, A2, up to some A sub capital N. And we define sequences of integers, P0, P1, P2, Q0, Q1, Q2, where P0 is A0, P1 is A1, A0 plus 1, and Pn is An, Pn minus 1 plus Pn minus 2 for all n greater than or equal to 2. So that gives us a sequence of numbers P sub n, or actually n going from 2, 3 up to capital N. You can't go any further than that. And Q0 is 1, Q1 is A1, and Qn is An Qn minus 1 plus Qn minus 2, also for n going from 2 up to capital N. And what we proved in problem 10 is that if you take the continued fraction up to some number little n, that's equal to Pn over Qn for all n going from 0, 1 up to capital N. So this is what is proved in problem 10. And what we want to prove here is that Pn Qn minus 1 minus Pn minus 1 Qn is always plus or minus 1. In fact, it's always minus 1 to the n minus 1 for n going from 1 up to capital N. Okay. Any questions about the statement of the problem?
Professor, so then we have to prove that the greatest common divisor of P of n Qn is 1, right?
That's the second part of the problem, right?
Okay.
One step at a time. This is the first thing. So okay. If you have no idea what to do, then one thing always to try is to prove by induction. So let's try to use induction. So for n equal 1, what does this say? It says calculate P1 Q0 minus P0 Q1. And we know what these four numbers are. P1 is A1, A0 plus 1 times Q0, which is 1, minus P0, which is A0, times Q1, which is A1. And you see, this is A1, A0 plus 1 minus A1, A0. That's just 1, which is minus 1 to any even power like 0, 1 minus 1. So it's true for n equal to 1. So the first step is to be able to do the case n equal 1. Just to give us a better feeling about what's going on, let's try the case n equal 2. When n is 2, we calculate P2 Q1 minus P1 Q2. We actually need to just calculate it. So P2 from our recursion formula is A2 P1 plus P0 times Q1 minus P1 times Q2 Q2 is A2 Q1 plus Q0. Well, I don't know. Let's see. Suppose we expand it a little bit and see what happens. This is A2 P1 Q1 plus P0 Q1 minus A2 P1 Q1 minus P1 Q0, right? This is all just high school algebra. I'm just expanding this. Now, A2 P1 Q1 minus A2 P1 Q1, they cancel. So what we're left with is P0 Q1 minus P1 Q0, which is almost what we had here, except the sign is reversed. So if I can write this as minus P1 Q0 minus P0 Q1. And we saw this is minus 1. That's what I just calculated. Sorry, this is plus 1. So this is minus 1, which is minus 1 to the first power, which is 2 minus 1. So this is the statement I want to prove. And here I prove this true for n equal 1. And here I prove this true for n equal 2. So now we need to do the inductive step. So suppose n is no bigger than n minus 1, and Pn Qn minus 1 minus Pn minus 1 Qn is minus 1 to the n minus 1. So what do we have to prove? We have to prove this statement when n is replaced by little n plus 1. That is, we have to prove that Pn plus 1 Qn minus Pn Qn plus 1 is minus 1 to the plus n. That's what we have to prove. Whoops. So questions about this? This is, if you're not used to doing sort of real mathematics, this is kind of maybe daunting, but.
Professor.
Yes, sir.
So this is what we are assuming, or what we want to prove?
This is what we assume this, the statement for n, and what we have to prove is the statement for n plus 1.
Okay, got it.
So what can we do? Well, Pn plus 1 Qn minus Pn Qn plus 1. Let me write down the expressions we have for Pn plus 1 and Qn plus 1. Pn plus 1 is An plus 1 Pn plus Pn minus 1 times Qn minus Pn, and Qn plus 1 is An Qn plus Qn minus 1. And if you expand, whoops, this should be n plus 1. If you expand, you get, so this is just, distributing across An plus 1 Pn Qn plus Pn minus 1 Qn minus this An plus 1 Pn Qn minus Pn Qn minus 1. And again, we're lucky we get this cancellation. Those two terms cancel. We have minus this plus this. So let me just write it in the opposite order. This is minus Pn Qn minus 1 plus Pn minus 1 Qn. All right, that's this term and that term. And if I take out the minus sign, this is minus Pn Qn minus 1 minus Pn minus 1 Qn. But by the induction hypothesis, this is minus 1 to the n. So this is, the induction hypothesis, this is minus 1 to the n minus 1. So we get minus 1 to the n minus 1. And minus 1 to the n minus 1 is minus 1 to the n. And everyone knows that n is n plus 1 minus 1. So we just proved the statement. So that's the inductive step. And we're done.
Professor, you don't have to do this question, but 13 is similar to that one. So we just follow the same steps, right?
Yes. But
Okay.
the second part of this problem.
But in that one, we start with n equals to 2, no 1.
Right.
Minus 2, no n minus 1.
Yeah, but it might be a little more complicated, but yeah.
Okay.
But also, so we have now this rule that Pn Qn plus 1 minus Pn minus 1 Qn is minus 1 to the n minus 1. And here we have Pn and here we have Qn. So if D divides Pn and Qn, this is divisible by D, this is divisible by D. So this is divisible by D, which means D can only equal plus or minus 1. So the greatest common divisor of Pn and Qn has to be 1. That follows from this formula. Because any common divisor of Pn and Qn would have to divide 1. All right. Questions about this?
No.
Okay. Any other questions? Any questions about the fundamental theorem of arithmetic? I proved that on Monday, but it's important that I want to go through it again. And so the fundamental theorem of arithmetic says the fundamental theorem of arithmetic says every positive integer is uniquely up to order a product of prime numbers. So, for example, 3 is 3. It's a product of 1 prime. 6 is 2 times 3. It's a product of 2 primes. It's also 3 times 2, but up to rearranging the factors, these are the same. This is what up to order means. If we wanted to write the primes in increasing order, then it'd be completely unique. 51, that's 3 times 17. 510. Well, if I can factor that, that's 51 times 10, and 51 is 3 times 17, and 10 is 2 times 5. So this is the factorization. If I write them in increasing order, it looks like that. So it's very important when you're studying number theory to spend some time just trying to factor integers. Right? I don't know, I'll make up a number, 3,196. No, 95. That's more interesting. How do we factor that? Well, I don't know. I'll give you a chance. Spend a minute and factor it.
Professor,
Yeah.
is 3 squared times 5 times 71.
Let's see. Well, certainly it's divisible by 5. Let me just do it step by step. If you divide 5 into that, that goes 639. And I can see this is divisible by 3. This is 3 times 213. And this is divisible by 3. 213 is 3 times 71. And I try to factor 71 and I can't. So this is the factorization. 3 squared, 3 times 3 times 5 times 71. Is that what you said? Just want to make sure I did it right.
Yes.
Yeah. So this is the factorization. What about this? 87691005283. Huh. Anyone want to try to factor that?
Nope.
Probably not. Now, if you took calculus at Lehman, Math 175 or 176, you had to take Math 155 and 156, the computer labs. And if you were lucky, you used Maple. So let me try something if I can. Share screen. So do you see this screen in front of you?
Yes.
See if I can make it bigger. So there's a command in Maple called ifactor for integer factor. So if you type ifactor 6, you get 2 times 3. If you type ifactor, what was the number we just did? 3195. You get 3 squared times 5 times 71. Let's see how good Maple is. Let's see if it can factor this number I just wrote down at random. 87691005283. Ah, who would have guessed? Well, believe me, you might have found by trial and error, 2 didn't factor it, 3 didn't, 5 didn't, but 7 did. But then you'd have some other huge number and you probably wouldn't try these numbers, right? In fact, I'm just sort of curious. If you take this number and you divide it by 7, this is what you get. So if I had given you this number and asked you to factor it, I mean, now we know what the answer is. It's going to be these three numbers. Yeah, there they are. It's pretty good. I mean, if you happen to have Maple, you can do a lot of number theory. Now, Maple claims that this number is a product of these primes. And how do you know that 3083 is prime? If you wanted to check that by trial division, that would take a while. There actually is another very useful function in Maple called isPrime. And you put in a number like 977, and it tells you whether this statement is true or false. 977 is prime, true. Let's take a number we know is not prime, like 6. 6 is prime, false. Wow, that's pretty cool. So, you can get Maple for free from the CUNY website. It's a very powerful program. And for lots of number theory, you can do lots of problems on Maple that you couldn't possibly do by hand. I mean, when I said factor 3195, that you can do by hand. If I say factor this, that you can't do by hand. It's just, I mean, you can, but you'd have to spend, a month or two with paper and pencil doing calculations and then correcting all your mistakes. So, yeah, it's pretty impressive, I think. Okay, anyway, so much for that. How many of you have actually used Maple before? I'm curious. Anyone?
I have.
I have tried, but I mostly use Mathematica.
Uh-huh. So how many of you took calculus at Lehman? Did you use Maple at all?
And Calc 1.
Lab?
Calc 1.
Did you use Maple? Some people use GeoGebra.
No, we use Maple.
Right, okay. Anyway, it's very, 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 very good, as you can see. Okay, anyway, the fundamental theorem of arithmetic says, first, you can write every number, a positive integer, as a product of primes. And second, that factorization up to order is unique. What about 1? So there's like a convention in mathematics. The empty sum, that is, the sum of nothing, is always 0. And the empty product is always defined to be 1. So 1 is a product of primes. It's a product of no primes, or the empty set of primes. So if you're happy with this notion, then the fundamental theorem of arithmetic applies to the number 1. If you're not happy with the notion, you can simply say the fundamental theorem of arithmetic says every integer greater than 1 is uniquely a product of primes. It really makes no difference, whichever formulation you like. I also had introduced the notion of a conjugate divisor. So let D be a divisor of n. That means n is equal to D times some number D prime, where D prime is n divided by D. And this is what is called the conjugate divisor of D. So for example, 2 is a divisor of 6. The conjugate divisor of 2 is 6 over 2, which is 3. Right? That's all. It's just a useful concept. There's also one other observation which is very important. I mean, this is known to the Greeks even. We'll talk about this soon. So suppose if n factors into d times d prime, where d and d prime are both between 1 and n, and I just choose d and d prime, so d is less than or equal to d prime. So if a number factors and d times d prime, and d is the smaller of the two factors, then in fact d is less than the square root of n. So the smaller, when a number factors into the product of two divisors, the smaller divisor is never bigger than the square root of n. And the proof is by contradiction. If n is d times d prime, and d less than or equal to d prime is strictly greater than the square root of n, then n, which is d times d prime, but both of these are greater than the square root of n. So this is greater than square root of n times square root of n, which is n. And you can't have n strictly bigger than n. That's absurd. So that's a proof by contradiction. If you assume that n factors into a product of two numbers, each bigger than the square root of n, you're led to a contradiction, this absurd statement. So whenever a number factors, the smaller of the two factors is no bigger than the square root of n. Can equal the square root of n, like 4 is 2 times, so if n is equal to 4, which is 2 times 2, 2 is equal to the square root of 4, or the square root of n. So the divisor can be as much as the square root of n, but the smaller divisor can't be any bigger. There's some other important notation that is used in number theory connected with the fundamental theorem of arithmetic. So suppose n is a positive integer and p is a prime. So let v sub p of n be the highest power of p that divides n. For example, if n is 6, which is 2 times 3, the highest power of 2 that divides 6 is 1. The highest power of 3 that divides 6 is also 1. The highest power of 5 that divides 6, well, 5 doesn't divide 6. So, of course, 5 to the 0 is 1. 1 certainly divides everything. 1 divides 6. So the highest power of 5 that divides 6 is the 0th power. And in fact, v sub p of 6 is 0 for all primes p except 2 and 3, all primes p greater than 3. Let's take another example. So suppose 540, that's a nice number. Factor 540, write 540 as a product of primes. and let me know what you get. Right.
You say to factor that number, right, Professor?
What?
You say that we have to factor that number, right?
Yes.
So it's 2 squared times 3 to the third times 5.
Okay. So you don't have to do it all one step. Like I look at this and I can say, well, that's obviously 54 times 10. And 10 is 2 times 5. And 54 is 2 times 27 times 2 times 5. And I know 27 is 3 times 3 times 3. So 2 times 2 is 2 squared, 3 cubed, 5 to the first power. That's the factorization. So for this number, 540, V2 of 540, the highest power of 2 that divides 540 is 2. The highest power of 3 that divides 540 is 3. The highest power of 5 that divides 540 is 1. The highest power of 13 that divides 540 is 0, because 13 doesn't divide this number. So 13 to the 0, which is 1, 0 is the highest power of 13 that divides this number. Any questions about this? This function VP of n has very interesting properties. For example, VP of m times n. If I want to know what is the highest power of p that divides m and n, that's going to be the highest power of p that divides m plus the highest power of p that divides n. So this is a very nice statement. What is, let me give a proof. Suppose I take m and I write it as a product of prime. So I know it's divisible by p to the v sub p of m times some number, I'll just call it m prime, where p and m prime are relatively prime. P doesn't divide m prime because p to this is the highest power of p that divides m. And n is p to the v sub p of n times some number n prime, where p and n prime are relatively prime. So if I take m times n, that's p to the vp of m, m prime, p to the vp of n, n prime. That's p to the sum of the exponents times m prime, n prime. And if p is relatively prime to m prime and p is relatively prime to n prime, then it's relatively prime to both. So the highest power of p, that divides mn is the sum vp of m plus vp of n. So if I wrote down everything I said, it takes more space, but that's exactly the correct idea for how to prove this statement. We've already talked a bit about the greatest common divisor of a pair of numbers or a set of numbers. So the greatest common divisor of integers a1, a2 up to a sub k is the largest integer d that is a common divisor of these. It's the largest integer d that divides each of these numbers, divides ai for all I from 1 up to k. And we denote this greatest common divisor by a1, a2 up to a sub k. So this is the largest number that divides all of these. We say that the integer m is a multiple of a if m is equal to a times q for some q. Right? M is a multiple of a, means like a, 2a, 3a, those are all the multiples of a. M is a common multiple of a set of integers a1 up to ak if m is a multiple of ai for all of these i's from 1 up to k. For example, if I let m be the product of all these integers, this is a common multiple. Right? For example, if I let a1 equal 4, a2 equal, I don't know, 18, a3 equal 7, then the number m equals 4 times 18 times 7, whatever that is a common multiple. Well, actually, let me make it easy. I just forget just have just two numbers, 4 and 18. So m equal 4 times 18, which is 72, is a common multiple of 4 and 18. But there are lots of common multiples. Moreover, m equal 36 is also a common multiple, because 36 is 4 times 9. 36 is a multiple of 4, and it's also 18 times 2. It's a multiple of 18. So 72 and 36 are common multiples. And just as for when we look at the common divisors of a number, we're interested in the greatest common divisor. When we look at common multiples, it's interesting to have the smallest. So, so there is the notion of the least common multiple of a set of integers. It's usually denoted LCM. So greatest common divisor is GCD, least common multiple, LCM, and we denote it by square brackets around the numbers. So for example, if I take A1 equal 4, A2 equals 18, the least common multiple of 4 and 18 is 36. The greatest common divisor of 4 and 18 is 2. And in fact, if you check, if I take the least common multiple of 4 and 18 times, the greatest common divisor of 4 and 18 times the least common multiple of 4 and 18, that's 2 times 36, which is 72, which is in fact 4 times 18. So that's an interesting relation. Suppose I take the following three numbers. A1 equals 4, A2 equals 18, A3 equals 14. So compute the greatest common divisor of these numbers and the least common multiple of these numbers. Right? So this is a problem for you to do right now. See, one way to do it, I guess, is to factor the numbers. So 4 is 2 times 2. 18 is 2 times 9, which is 2 times 3 squared. 14 is 2 times 7. So the number 2 clearly divides all three of these numbers. 2 squared doesn't divide 14 or 18. 3 doesn't divide 4. 7 doesn't divide 4 or 18. Any other prime doesn't divide any of these. So just by looking at the factorizations, you see that 4, 18, 14, the greatest common divisor has to be 2. And if a number is a multiple of each of these, the number has to be divisible by 4, has to be divisible by 9, has to be divisible by 7. So the least common multiple has to include 2 squared, 3 squared, 7. That's 4 times 9 times 7. See, if you multiply that out, that might even be 252. Let's see. 4 times 9 is 36. 36 times 7 is 252. Yeah, that's the least common multiple. And again, it's interesting that if you multiply 4 times 18 times 14, you get 504, which is 2 times 252, which is the greatest common divisor of these numbers. times the least common multiple. Well, just so everyone can have some fun. Suppose I take the numbers 294 77 and 56. So compute the greatest common divisor and the least common multiple. Yeah, I would say spend a minute or two with that. Be kind of interested. Any success?
Yes.
Okay. What is the GCD?
7.
7?
Mm-hmm.
Um,
294 is 2 times 3 times 7 squared.
Okay, so
77 is 7 times 11. And 56 is 2
you know
to
what
the
the
third
greatest
times.
common multiple is? That's a lot bigger.
Yes, that is 2 to the cube times 3 times 7 squared times 11. 3, just 3, 7 squared times 11. And that is 12,936.
Right. So let's see. How could we do that? 294, if you divide it by 7, you get 28. 7 times 42, is that right? Which is, and 42 is 6 times 7, 2 times 3 times 7. So 294 is 7 squared times 2 times 3. 77 is 7 times 11. And 56 is 7 times 8, or 2 cubed. So the only common factor of these three numbers is 7. And the least common multiple, you have the highest power of 2, which is 3. The highest power of 3 is 1. The highest power of 7 is 2. And the highest power of 11 is 1. That's very good. Now, if, again, you have maple, remember in maple, there was this command I factor. That means factor the integer. If you just use the command factor, that's the command for factoring a polynomial. So, oops, I need to share the screen with this somehow. Share screen. No. Right. So you can see the maple now? Good. So I factor is the command to factor an integer. That means integer factor. You just say factor, that's the command for in maple for a polynomial. So we have I factor, factors an integer. Is prime tells you whether a positive integer is prime or composite, true or false. There's also a command for finding the integer greatest common divisor, IGCD. That means integer greatest common divisor. For example, if I take 6 and 21, the greatest common divisor integer is 3. If I want the integer least common multiple of 6 and 21, that's 42. That's pretty good. What about the problem we just had? We had the numbers 294, 77, and 56. So if I want the greatest common divisor of these numbers, that's 7, just like I was just told. If I want the integer least common multiple, that's this number. Let's see. Someone gave this to me as in its factored form. Suppose I factor this. I factor, and then in maple, percent sign means the last thing we calculated. So this will be factor this number. Exactly what someone told me. 2 cubed, 3, 7 squared, 11. So yeah. Maple's pretty good for number theory. It may be, I'm going to have to think about this. I'm going to ask everyone to download Maple from CUNY. You get it for free. It's good for a year. And I'll show you how to use these simple commands, and you can solve a lot of number theory problems. It's fun doing things by hand, especially for small numbers, but often for big numbers, the only way to do it is with a computer. Okay? I mean, if I take numbers, I don't know. Actually, these are just some random numbers I'm writing down. And there they are. If I want to know what is the greatest common divisor of these numbers, they're relatively prime. Okay, well, there's no way to guess that that's the answer. I mean, this is just, I mean, there's a way to compute this, of course, using the Euclidean algorithm. You find the greatest common divisor of the first two and take the greatest common divisor of that with the third. But Maple gives it to you in less than a second, obviously.
Professor,
Yeah.
we will be able to use Maple in the exam?
For some things, yes. Yeah, I just
Okay.
changed the numbers a little bit. So you can tell by looking, each of these numbers is divisible by 2, but not divisible. They're not all divisible by 4. That's kind of interesting.
Professor,
Yeah.
so 12,936, right, times 7 doesn't give you the same value as if you were to multiply all the numbers together.
Well, let's do the experiment. You're saying 7 times 12,936. That's 9,552, right?
Yes.
And if I multiply the 3 numbers together,
You get like
294,
a million something.
77 times 56, I get something different. So your observation is correct. When I have 3 or more numbers, the product of the greatest common divisor and the least common multiple are not the same numbers. That's only correct when you have 2 numbers. So for example, suppose I take $294 and 77. That's the GCD. And the LCM is 3234. And 7 times 3234 is 22,638. And if I take 294 and multiply it by 77, I also get 22,638. So that statement that the product of the GCD and LCM equals the product of the numbers is true when you have 2 numbers, but it's not necessarily true for more than 2 numbers.
Okay, understood.
Right. So for 2 numbers, that's a theorem. For 3 or more numbers, it's not true. Okay. Oh, good. Let's keep going. This is kind of fun. So by the fundamental theorem of arithmetic, FTA, any number n, you can write as a product of prime powers, and two to some power, three to some power, five to some power, and so on, forever, really. So I can use product notation. N is a product over all primes P, the power P to V sub P of N, where V sub P of N is 0 if P does not divide N. I mean, this looks like an infinite product, but a positive integer is only divisible by finitely many primes. So from some point on, each of these exponents is 0, P to the 0 is 1. You're just multiplying by 1. So this apparent infinite product always does converge. So if you have, let's just look at two numbers. Suppose A1 is some number. This is P to the VP of A1, P to the VP of A2, and so forth. That's not the way I want to write it. I want to write this out explicitly. So this is 2 to some power, 3 V2 of A1, 3 to the power of V3 of A1, 5 to the power of V5 of A1, and so on. P to the power of V sub P of A1, where these factors are all 1 from some point on. I have another number, A2. That's 2 to some power, 3 to some power, 5 to some power, P to some power, and so forth. So what is the GCD of A1 and A2? If a number divides both of these integers, like the power of 2 in that divisor can't be bigger than either of these two numbers. And the biggest it could be is the smaller of these two. So this would be 2 to the smaller, the minimum of V2 of A1 and V2 of A2. And similarly, the highest power of 3 that divides these numbers is the smaller of these two numbers, the minimum of V3 of A1 and V3 of A2. And in general, for any prime P, the highest power of P that can be a common divisor of A1 and A2 is the minimum of VP of A1, VP of A2, and so forth. So we have a kind of formula for the GCD. The greatest common divisor of A1 and A2 is this product over all primes P. P to what power? The minimum of VP of A1 and VP of A2. If we think hard about this, we can see there's a similar kind of formula for the least common multiple of A1 and A2. Because if a number is divisible by A1, it's divisible by this product. So it's divisible by 2 to this power. It's also divisible by 2 to this power, which means it has to be divisible by the larger of these two numbers or anything bigger. Sorry, any number that A1 and A2 divides is divisible by both of these powers of 2, so it's divisible by the larger. This is like 2 to the maximum of VP of A1, VP of A2, and so on. We get this infinite product over all the primes P of P to the max of VP of A1, VP of A2. So this is a special case of the theorem in section 1.4, theorem 111, which extends this to any number of factors. But just looking at 2, we have the following observation. Suppose you have 2 numbers like X and Y. Let's say they're real numbers. And suppose X is less than or equal to Y. So the minimum of X and Y is X, and the maximum of X and Y is Y. So if I take the minimum of X and Y times the maximum of X and Y, that's the product of X times Y. So for any 2 real numbers, positive, negative, 0, doesn't matter. For any 2 real numbers, I have this kind of simple rule. I also have the same kind of rule. Actually, this is true, but actually I'd rather do this for addition. Suppose I take the minimum of X and Y plus the maximum of X and Y. That's equal to X plus Y. Right? If I have 2 numbers, one of them is smaller and one of them is larger, so the sum is the sum of the 2 numbers. If the 2 numbers are equal, this is just X plus X equals X plus X. But if X is less than Y, this is X plus Y equals X plus Y. If Y is less than X, this is Y plus X equals X plus Y. That's all true. So for any prime P, if I have something like P to the minimum of V sub P of N, V sub P of M, times P to the maximum of V sub P of N, V sub P of M. By the rules for exponents, P to a power times P to a power is P to the sum of the powers. But the min of 2 numbers plus the max is just the sum of the numbers. So that's P to the VP of N plus VP of M. So if I take the greatest common divisor of 2 numbers, A1 and A2, times the least common multiple of those 2 numbers, the GCD, the greatest common divisor, is the product over all primes, P to the minimum of VP of N, VP of M. And the least common multiple is the product over all primes, P to the max of VP of N, VP of A1, VP of A2. And again, this is the product over all primes, P to this plus this, just by our rules for exponents. So this is the product over all primes of P to the VP of A1 plus VP of A2. This is the product over all primes, P to the VP of A1, product over all primes, P to the VP of A2. This is just A1 times A2. So if you like, this is a proof of the formula that for two numbers, the greatest common divisor times the least common multiple is the product of the two numbers. That's just a very pretty formula. All right. Okay. There's one more theorem in this section that I want to cover right now. So there's just some more notation that x be a real number. For example, x is square root of 2. The integer part of x, which is denoted by x with square brackets around it, is the greatest integer less than or equal to x. So you remember square root of 2 is 1.414 something. So the integer part of which is between 1 and 2. So the largest integer, no bigger than that, is equal to 1. And the fractional part of x is x minus the integer part. It's the part greater than or equal to 0 and less than 1. So the fractional part of the square root of 2 is, take away the integer part, 0.414 and so on. Right? That's the integer part and the fractional part. So for example, the integer part of 7.29 is 7, and the fractional part of 7.29 is 0.29. The integer part of -3 minus 7/2, see on the number line, 0, -1, -2, -3, -4, -7/2 is right there. What's the greatest integer less than or equal to -7/2? It's -4. And what's the fractional part of -7/2? It's the integer part minus the number. So that's 4. That's -4. Oops. Sorry, it's the number minus the fractional part is the number when you take away the integer part. So it's -7/2 minus the fractional part of -7/2, which is -7/2 plus 4. That's 4 minus 3.5. That's a half. Right? So for -7/2, the integer part is -4 and the fractional part is a half. So Theorem 112 as for the factorization of n factorial. So if you want to, so n factorial 1 times 2 times 3 is the product of all the positive integers up to n. If you want to factor this, you have to know for any prime, what power of the prime divides this number. That is, what is for any prime p, what is v sub p of n factorial? And the theorem says you take the sum over all r of, take n divided by p sub r, that's not an integer, but you take the integer part of that. As r goes from 1, well, you can say it goes from 1 to infinity, but of course, you can note n over p to the r is positive, and n over p to the r, at some point as r gets bigger, this denominator gets bigger, so this fraction is less than 1. It's less than 1 if n is less than p to the r, or if log n is less than r log p, or if r is greater than log n over log p. So as soon as this integer r is greater than log n over log p, n over p to the r is less than 1, and this is 0. So you can either say this goes up to infinity, or up to the point, the last point of which is positive, which is the integer part of log n over log p. That's the way it's written in the text. So this is a formula for the power of a prime dividing n factorial. Let's just do a calculation. Suppose I want to know a huge number, like 10 factorial. That's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. That is a big number. What is the power of 3 that divides 10 factorial? By this formula, so here we have p equal to 3 and n equal 10. This is a sum over r for n, which is 10 over 3 to the r. Now, r can be 1, r can be 2. Once r is 3 or greater, this is 0. So just r going from 1 to 2. That's the integer part of 10 over 3 plus the integer part of 10 over 3 squared, or 9. 10 over 3, that's 3 and a third. This integer part is 3. 10 over 9, the integer part is 1. So this is 4. So this says 3 to the 4th divides 10 factorial. 3 to the 5th does not divide 10 factorial. Right? In fact, if you take a look at this, what are the powers of 3 and 10 factorial? I have, what are the multiples of 3? I get 1 3 here. From 6, I get 1 3. That's 2 3s. From 9, I get 2 3s. So that gives me 4. So 1 plus 1 plus 2 is 4. That's exactly right. Suppose I want to know the power of 2 that divides 10 factorial. Let me just look at this. I have a 2, 2 2s, 1 2, 3 2s, and 1 2. So I have 1 plus 2 is 3, plus 1 is 4, plus 3 is 7, plus 1. This should be 8. Let's see what our formula, so we know the answer is 8. Let's see what the formula says. This is a sum over r of 10 over 2 to the r, integer part. So that's the integer part of 10 over 2 plus the integer part of 10 over 4 plus the integer part of 10 over 8. And the integer part of 10 over 16, that's 0. 10 over 2 is 5. 10 over 4, that's 5 halves, that's 2 1/2. 10 over 8, that's 5/4 is 1. We get 8, which I think is just what I calculated a moment ago. So for a small number like 10 factorial, that's what it is. So how do we prove this formula? So what is the proof that VP of n factorial is the sum of the integer part of n over p to the r going from 1 to infinity, or log n over log p? So remember, n factorial is 1 times 2 times 3 m all the way up to n. It's the product of all the numbers from 1 to n. So let's say one of them is m. So if p to the r divides m, then p to the r is certainly less than or equal to m, which is less than or equal to n. So if I take logarithms, r is less than or equal to log n over log p. And since r is an integer, it's less than or equal to the greatest integer in log n over log p. So one way to write this is VP of m. So this is the highest power of p that divides m. And the highest power is at most log n over log p, integer part. So as r goes from 1 up to log n over log p, if p to the r divides m, that's 1. So for example, if p cubed divide m for r equal 1, p divides m. For r equal 2, p squared divides m. For r equal 3, p cubed divides m. So you get 1 plus 1 plus 1. If p4 doesn't divide m, then once you're past r equal 3, you don't get any more. So this is exactly counting the highest power. It's a funny way to write it, but that's the highest power of p that divides m. And how many integers up to n are divisible by p to the r? So the number of integers less than or equal to n divisible by p to the r, let's see, what would they be? You'd have 1 times p to the r, 2 times p to the r, 3 times p to the r, up to, let's say, k times p to the r. But k plus 1 times p to the r would be too big. So the number of integers up to n divisible by p to the r is this number k. K is at most n over p to the r, which means the integer part of that. So the number of integers up to n divisible by p to the r is exactly the integer part of n over p to the r. So this is the proof that's in the book, VP of n factorial. The highest power of p that divides n factorial. So by the addition rule, this is the sum for every m from 1 up to n, VP of m. What is VP of m? Here's the formula. So this is the sum, m goes from 1 up to n. The sum, r goes from 1 up to integer part of log n over log p, p to the r dividing m of 1. Let me interchange my summation. This is r goes from 1 to log n over log p. M goes from 1 up to n for all p to the r that divides m. 1. Let me just try to explain what this means. So for every m from 1 up to n, we look at the number of r's up to log n over log p, where p to the r divides m. So r goes from 1 up to log n over log p. And whenever you have a number m where p to the r divides m, you get 1. And then this is just the number of multiples of p to the r up to n. This is summation, r goes from 1 up to log n over log p, n over p to the r. That's the formula. Now, again, this is quick and easy for me to write down, but you really need to understand the justification for every single step. Every equal sign is a statement that requires a proof. And this involves, a lot of thinking, really. That's what it is. Right. I saw in the chat that someone wrote that you need Microsoft 360 to download Maple. So I've downloaded Maple from the CUNY website, and I don't know what Microsoft 360 is. So either I have it on my Mac and I used it without knowing it, or you really don't need it. I just don't know. But I had no trouble downloading Maple. And I teach 2 sections this semester of Math 156, which is calculus with Maple. And none of my students had a real problem downloading it. So it can't be that hard to do.
Professor,
Yes.
I just put it at the link where I just downloaded. I already have it. So that link that I put it, you don't need Microsoft 360 to download it.
Right. So you don't need it. Good. Thank you. Yeah. So if you go to the chat, you see that, yeah, you don't want to go to maplesoft.com free trial because they're not going to give it to you for free. You go to offers.cuny.edu. That's the CUNY website where you get Maple. And the only thing you have to remember is when you're downloading it on the website, it gives you some code you need to enter to validate the program. So make sure when you go to that site to download it, you also write down the secret number they give you that you have to enter when you actually try to run it the first time. And the only problem students in my Math 156 classes have had is they forgot to jot down that secret code and they just had to go back and get it. Okay. All right. That's it for today. I have an office hour scheduled this evening at a Zoom office hour at 7. And I'm also going to have one on Friday afternoon. I'll post that shortly.
Professor,
Yes.
before we go, there's a homework question that is asking about standard factorization with factorial numbers. So what do you mean about standard factorization?
Sorry, which problem is it?
Guys, I think it's problem 5 from page 30. I'm not sure. Let me check.
All right, compute the standard factorization of 15 factorial.
Yes.
Right. Well, so what that means is 15 factorial, that's 2 to some power, 3 to some power, and so forth. Actually, the only primes that divide 15 factorial are 2, 3, 5, and 7. And you have to compute these exponents. And you compute them from the theorem. So for example, what is V7 of 15 factorial? That's going to be 15 over 7. 7 squared is too big, is 2. So this is just 7 squared. The power of 7 is 2. But you use the theorem to compute these powers.
Okay, got it. Thank you.
Okay. Anything else? If not, then we're done for today. The next class is Monday, but I do have a couple of Zoom office hours this week. Okay, bye all.
Bye, Professor. Have a good day.
Thank you. You too.